Hi, everybody. How are you guys?
Good.
So today we're going to be starting chapter 14. So chapter 14, we're going to be talking about rational functions. So when we talk about a rational function, the way we define a rational function is some p of x over q of x, where p and q are polynomials, and q is non-zero. So this is convenient because what have we just got done studying? Polynomials. And what is a rational function? Polynomial divided by another polynomial, right? So it's just like the quotient of two polynomials. So we're going to start talking about like identifying the key features of a rational function. So there's kind of 8 key features that we're going to talk about here today. So there's going to be the domain, vertical asymptotes, horizontal asymptote, other asymptotes, removable discontinuities, x-intercepts, y-intercepts, and the end behavior using a limit as a descriptor. So we're going to kind of group these features together because at some point we're just going to like give you a rational function, ask you to find all these things, and then use them to kind of build the graph. Before we start going all the way there, we're just going to worry about how do we find these things for starters. So that's what we're going to focus on today. I've kind of grouped them together. The color coding is me grouping the things together that I kind of would do all at the same time. So like if I'm going to worry about finding the domain, I might as well find the vertical asymptotes and removable discontinuities kind of all in one shot. Because in the process of finding one, I'm like right there to find the other one. Or if I want to find my horizontal or other asymptotes, if I'm going to find one, I might as well find the other. Or x and y intercepts, or I kind of pair these things together that make, I think, the most sense. And kind of, I'm going to find these things all in one shot. Everybody cool with the plan? So I'm just going to kind of go through and do some examples where we find these key features. I talk about how to do it, how to look for each of them, and then we'll go through and do the example, and that's going to be that for today. Sound okay? All right. So our first example. Here is x minus 2 over 3, x squared minus 3x plus 2. My first step, regardless of what we're going to be, or this first example, we're going to be looking for domain, and then vertical asymptotes, and removable discontinuity. So on this step, and really for all of these problems, my first step is usually going to be try to factor this as much as we can. Okay? So, can I factor x minus 2 in? Why not?
Can't have you can't have the x. You can't have the 2 the 2 x and the x2.
So I would say because it's a polynomial that's degree 1 and leading coefficient 1, right? Because it's just x, 1x to the first. If you have something like that, there's no factoring that I can do with that, right? If its leading coefficient is a not 1, maybe there's a greatest common factor. If the power is not 1, maybe I can do some factoring like we talked about in the previous chapter. But if it's just 1x to the first, there's nothing I can do with that, right? How do I factor x squared minus 3x plus 2?
Sure, factor, so you find x multiplied to 2 and add to negative 3.
Great, and those two things would be?
Negative 2 and negative 1.
Good. Okay. Once I have it factored, we're going to find the domain now. Okay? When I divide two numbers, which is what we're doing right here, we have a fraction, we have a top divided by a bottom, right? When does division fail? When does division not work?
Oh, when one of the numbers is 0.
Not when one of the numbers is 0, specifically when the denominator is 0. So we take the denominator we set it not equal to 0 and solve. Okay? Because I know if I'm dividing two numbers, if I divide by 0, that doesn't work. Right? So I need to figure out, okay, well, what gives me a divide by 0? So 1 and 2, right? Those would be the values of x that would give me a 0 denominator. So the domain cannot contain those numbers. Pretty good. Let's write this as this domain now using like a interval notation, with parentheses and brackets. So if I want everything except for 1 and 2, what are the intervals that I need then? Everything less than 1, but not including 1, or not everything greater than 1, everything from 1 to 2 though, and then everything greater than 2. Everybody okay with what I've done there? Notice that those are those U's stand for or. That's the union symbol. Is everybody okay there? Okay. Now I'm going to reduce this fraction. Is there any reducing I can do to this? Yes,
X minus 2's cancel out.
the x minus 2's can cancel out. What am I left with then?
0 over x minus 1.
1 over x minus 1. Everybody okay here? So the next thing I'm going to do is I'm going to find my removable discontinuities. I'm abbreviating that RD. RD is short for removable discontinuity, or holes. Okay? So a hole in our graph is created when we eliminate completely a factor from the denominator of our fraction. So for a removable discontinuity to exist, reducing has to take place, and that reducing must eliminate all of those factors. So in this case, did we do any reducing?
Yes.
Yes. What did we reduce?
X minus 2.
X minus 2. Are all the x minus 2's gone?
Yeah.
Yes. That means that we have generated a removable discontinuity. we're gonna take our reduced denominator, set that equal to 0 and solve. What do I get here? Oh, I'm sorry, no. I did a bit. Set any factors completely reduced from the denominator. What factor was completely reduced?
X minus 2.
X minus 2. Oh my goodness, guys. Okay. Sorry. Big mistake there. So what's my solution?
X equals 2.
X equals 2. Now, this needs to be a point. The removable discontinuity is a point. So we have its x-coordinate. The x-coordinate is 2. How do I find its y-coordinate?
Substitution.
Plug it back into the reduced.
It's 1. It's 1.
Yeah. So our answer here should be the point 2, 1. Does everybody feel okay here? Good? Okay. Next, we're going to talk about finding the vertical asymptotes. Your vertical asymptote is going to be an equation. It's going to be an x equals equation. To find that vertical asymptote, we're going to set the reduced denominator equal to 0 and solve. That's our vertical asymptote. Okay? Notice that if I look at the values that are not in the domain, those x values have to be the x's for my hole, my removable discontinuity, or my vertical asymptote, right? But all of these values have to be in one of these two places. Everybody's okay? You can't have not equal to 3 and the 3 not be either an x coordinate for removable or a vertical asymptote. Does everybody feel okay on this? You see why I group these 3 skills together? Because once I do the reducing, I'm going to get factor and reduce, I'm going to get all the answers I need, right? The thing to remember is that you have to find the domain before you reduce. But that's all. Everybody feel okay? Okay. The next thing we're going to talk about are going to be finding horizontal asymptotes and other asymptotes. I'm going to talk about how to do this first. I'm going to draw like a flow chart to help us kind of remember how to do this before we do the examples. Everybody's okay? So this works, I think, well to just see it in action, because when I write this stuff down, if you don't see the example at the same time, it's not super clear what it is I'm talking about. But I think this one's fairly clear. So every rational function is either going to have one horizontal asymptote or one other asymptote. It'll never have both. It'll never have more than one of each. Okay? It's either going to be one horizontal or one other, and never both at the same time. Never 2 or more of one of them. Okay? You can have all the vertical asymptotes you want. There's no limit there. Here there is. Okay? So you're only looking for one of a horizontal or other asymptote. Is okay? So to do this, all we need to do is we need to compare the degree of the numerator with the degree of the denominator. And that'll tell us what we need to do. So if I'm comparing the degree of the numerator with the degree of the denominator, there's three possible outcomes. What are the three possible outcomes? The numerator could be bigger, could be smaller, or it could be equal. Everybody's okay? So I'm going to start from smaller to bigger. The degree of the numerator is smaller than the degree of the denominator. Always one horizontal asymptote, and the equation for the horizontal asymptote is always y equals 0. So the degree on top is smaller, horizontal asymptote y equals 0. Done. Nothing more to do. Right, okay? If the degree of the numerator is equal to the degree of the denominator, then again, it's a horizontal asymptote. It's not the same every single time. It's going to depend on the equation, but it's easy to come up with. So horizontal asymptote is going to be y equals leading coefficient in the numerator over leading coefficient in the denominator. That's what LC is abbreviating, leading coefficient. Again, easy to do, right? You can do it just by inspection. Looking at the equation is all you need. Oops, sorry. I touched something. The last situation, if the degree of the numerator is greater than the degree of the denominator, that's going to be our other asymptote situation. That's the worst one to come up with. So that's always going to be the equation with an x in it. So it's going to be the equation of a line or a parabola or a cubic or something. It's going to be the equation of some polynomial. The way we get that equation is it's going to be the quotient of the polynomial division, numerator divided by denominator. So we have to do a polynomial division to get the equation of the other asymptote. Typically in a class like this, it would be a line. Maybe somewhere in the homework there's a hard one, it's like a parabola. But it wouldn't get harder than that in this class like this. Everybody's okay? Let's do some examples now. I'm going to do one example of each case. Very good? You got what you need from here? Okay. Okay. So if I look at the first one, what I need to do to decide what's going on is I need to compare the degree of the numerator and the degree of the denominator. What is the degree of 2x minus 3?
1.
1. How'd you get that, Mark?
Yes, doesn't have an exponent anymore, it's just 1.
It's x to the first. The degree of the denominator is?
1.
1. So the degree of the numerator is equal to the degree of the denominator. I'm just going to write an equal sign there. Is everybody okay with that? The rule says that means we have a horizontal asymptote, and the equation should be y equals the leading coefficient of the numerator, which is 2, over the leading coefficient of the denominator,
1.
which is 1. So y equals 2. How'd that feel? Okay, what's going to be the hard part? Just remembering the rules, right? The actual arithmetic, the algebra that we're doing, pretty easy. Remembering what to do for which one, that'll be the hard part, right? Just keeping everything straight. All right, the next example. What is the degree of the numerator?
1.
What's the degree of the denominator?
2.
Which situation is this?
3.
Well, it's the less than situation, right? So we'll write less than. Degree of the numerator is 1, which is less than the degree of the denominator, which was 2. What is the rule for that situation? Says we have a horizontal asymptote, And the equation will always be
Y is equal to 0.
y equals 0. That's the easiest one because there's nothing to calculate. Once I see smaller on top than bottom, y equals 0.
So if the bottom has, oh, okay, never mind.
The bottom is degree 2 because it's x squared. The top is degree 1 because it's x to the first.
So there's no calculating that ever, like it's always just 0?
It's always y equals 0. Yep. Which is nice, right? Okay, let's look at the last one. The degree in the numerator is
2.
2. The degree in the denominator is 1. This is the greater than situation. This is the tough one. It says to find the equation now for this asymptote, I need to do polynomial division. So if I look at the problem, I need to do x squared plus 3x plus 2 divided by x minus 3. There are two ways to do polynomial division. Long division that works every single time, and synthetic division that works in special cases. Now, if this is one of the special cases, please let me do the synthetic division because it's a lot quicker and simpler than the long division. But we need to check first before we start plowing into synthetic division, right? What do I need to have in order to do synthetic division? The divisor, or in the case of a fraction, the denominator, needs to be degree 1, check. Leading coefficient 1, check. Synthetic division okay here?
Yes.
Everybody's okay? If it wasn't both of those, you have to do it as long division. Or you should, I should say. Okay? All right. So, I set x minus 3 equal to 0, and I write the solution on the outside. And then on the inside, I'm going to have the coefficients from the numerator. Is everybody okay with my setup? Okay. Very good with the synthetic division that I did. Bless you. So remember, remainder, constant, x coefficient. This part right here, the part that doesn't include the remainder is the quotient, right? So my other asymptote is y equals x plus 6. Because the quotient of that division was 1x plus 6.
So you don't care about the...
The remainder tells me nothing! Yeah. Unless it was 0, in which case it'd be like, well, okay, then this thing just reduces down to a linear equation. You know, the equation of a line, which is, I guess that's something, but as long as it's not 0, it doesn't really mean a whole lot to me. How do we feel on these? Again, none of the procedures was terribly time consuming, but there's a lot of them, right? There's a lot of possibilities that can happen, and the procedure's a little bit different for each one. Recognizing what to do should be easy. All you're doing is comparing degrees of the numerator denominator. The individual procedures themselves are fairly easy, but there's 3 to remember, and you have to remember which one goes to which, right? And that tends to be the hard part. Are you okay? The good news is, what do you guys have for your test? No, right? Which makes remembering which one goes with which a heck of a lot easier, because you can write it down. How are we feeling? So far, so good? Okay. Next one we're going to do are finding x and y intercepts. So to do this, for the x-intercept, So the x and y intercepts are both going to be points. They're going to be ordered pairs. They're going to be an x and a y. For the x-intercept, you're going to plug 0 in for y, and then compare the reduced numerator to that. Because when is a fraction equal to 0? When the numerator is 0, right? When the top is 0, as long as the bottom isn't, right? And the bottom can't be 0 because we'll have reduced it when we do it, so we'll be fine. For y-intercept, again, you're going to take the reduced form, and you're going to plug 0 in for x. And that's should be it. That's all we need. Everybody good? Let's do the example. All right. Can I reduce the numerator at all?
No.
No, right? Why not?
Because it's right.
Degree 1 leading coefficient 1, right? Can't do anything with that. How about the denominator? X squared minus 3x.
Take it on x.
Yes, there's a greatest common factor here. I can take out an x. Now, let's look for reducing. Is there any reducing I can do?
Take out the x's.
I can reduce out the x. And remember, when I reduce these, they become 1s. So if I want the x-intercept now, I'm going to take the reduced numerator, which is just 1, and I'm going to set that equal to
Y.
0, right? Because 0 is going in for y. Does this have a solution? What does that tell me? I don't have an x-intercept here. That's fine, that happens, right? How many x-intercepts can one of these rational functions have? 0 to as many as you want. Now, you probably aren't going to see a situation that there's more than 2 or 3 of them, but like in theory, I could write you one that has like 1,000 x-intercepts if I wanted to, but like, goodness me, you're not actually going to do that. So far, so good? Okay. For the y-intercept, I'm just taking my reduced function here, 1 over x minus 3, and I'm plugging 0 in for x. So my y-intercept is just 0 comma negative 1/3. How do I know negative 1/3 is the y-coordinate? It literally says y equals, right? Of course it's got to go in that spot. I have another example doing this to see one where we actually get some x-intercepts, but I feel like it's worth doing one where there's no x-intercept that happens and pointing out that like, hey, that can happen. When we do y-intercepts, how many y-intercepts can we have? 0 or 1. You can have no y-intercepts, that's okay. But 0 or 1. Okay. But no more. All right. So, what do I start by doing?
Seeing if you can.
Starts with an F.
Factor.
Factor. Okay, x squared plus 4x plus 3, does that factor?
Yep.
Okay, what does it factor to?
3 plus 3.
Okay, x plus 3, x plus 1. And then x squared plus 5x plus 4.
Positive 4 and positive 1.
Okay, x plus 4 and x plus 1. Does anybody have a question how Mark is doing that so quickly? Do we need to run through how to do that again? We just got done talking about factoring polynomials in the last chapter. Hopefully, like a quadratic with leading coefficient 1, we still feel pretty confident in factoring those. That was a mastery level skill from Algebra 2. We hope we can still do that quickly and efficiently. Or the expectation is you are still able to do that quickly and efficiently. If you're not, find some time to come talk to me and we can go through it again. And very cool. Whoa, boy, in detail and make sure we get you up to speed. Note that we had an x plus 1 in that top and bottom. I reduced those, leaving me with just x plus 3 over x plus 4. Is everybody okay with that?
Yes.
Okay. For the x-intercept, what do? I take the reduced numerator and set it equal to 0. Done. That's it. There's my x-intercept, negative 3, 0. Remember, x-intercepts are points, right? Krista, you want to say something, I can tell.
So then, do you not have to do anything with the leading coefficient?
The leading coefficient does not matter to me.
Why?
Why just,
Well, yeah, for that, but did you not have to do it up there, like for anything
for anything?
in this problem?
When you say leading coefficient, do you mean degree?
Yeah, like the,
So if I was asking for like, to identify all the key features of this, then yes, we talk about horizontal and other asymptotes and stuff, and we would want to look at the degrees. Here I'm just doing an example where I'm just talking about x and y intercepts. Is that okay? Okay. And this tends to be like the way I like to separate out the test is not every problem is going to be like, give me all the key features, but like, here's a problem, give me this specific feature. Here's a new problem, give me this specific feature. Because if you muck up one problem, like everything is going to be wrong, right? Like if you factor something wrong, every part of it's going to be wrong afterwards because of that. So like, I try to separate them out, so I'm doing the example of separate. Now, the expectation is like, I could give you then like, after we've done these like as standalones, give you one where I ask you to find all the features. And like, or here's all the features and like, draw me the graph for this or something, but this is only looking at 2 of the features, just x and y intercepts. So I don't care about the degrees for that. Cool? Okay. And then for the y-intercept, we just plug 0 in for x. Oops. Oops. And we're done, right? These tend to be the easiest two, because there's not really much to do here. It's usually just solving like a simple little linear equation. But again, you have to remember which one is which and which one, which do I plug the 0 into x or y, but they're usually like, if you can keep everything straight, it's easy. So far, so good. Last thing to talk about are end behaviors. What I want to do here, we'll do end behavior again in the next lesson. I want to do starting from the graph and building the end behaviors from this rather than from the equation and getting the end behaviors from the equation. And just try to separate this into 2 days worth of a skill because just feels like that's what it is. Sure. Just to like separate the skill out a little bit. All right. All right, so here's a graph of a rational function. Okay? Remember what end behaviors are describing is what the arrows on the graph are doing, right? If I look at this graph, how many end behaviors am I going to have? 4. because I have 4 different arrows on my graph. I've labeled those specific end behaviors A, B, C, and D just for making the communication easy. Is everybody okay with what I've done? Okay. So remember, my limit notation looks like this every single time. I'm just going to be filling in these 2 blanks. X approaches something, and then the limit of f of x equals something, right? The x approaches is what the x coordinate is doing with the arrow, and the equals, f of x equals, is going to be what the y coordinate is doing. All right? So if I look at this arrow is pointing to what x coordinate? Negative infinity. Everybody is okay? Because it's pointing straight to the left. And in the x direction, that's where negative infinity lives. Okay. And then what y coordinate is that arrow pointing to? Not positive infinity, because it's not pointing up. It's like flat. Not 0, because this is x equals 0, or y equals 0.
Oh, it's 2.
It's going to be y equals 2. Right? Because this line is y equals 2. That's what it looks like it's pointing towards. I know. It's far, you're far away. Is that okay? Let's do B. Okay? What x coordinate is that arrow pointing to?
2, 3, 1.
1. Okay. And then what y coordinate is that arrow pointing to?
Positive infinity.
Negative, because it's pointing down. Yeah. Okay. All right, let's look at C. What x coordinate is C pointing to?
1.
1. And what?
Positive infinity.
Yes. Now you're on it. Okay. Now there's something wrong with what we've done. Now, you wouldn't have known any better, because this is the first time doing this and running into this situation. I know better. So what we've written here is not completely correct. Can anybody see the issue that we're having?
Oh, never reach. Never like hit the x values where the defined values that aren't infinity.
I'm not sure what you mean there.
Like it'll never hit 2, it'll never hit.
Oh, that's fine.
Oh.
I'm not worried about that. This is a function, right? If I have a function, can an x value have 2 different y values?
No.
No. But that's kind of what we're saying is happening, right? We head to 1 and we go to negative infinity. We head to 1 and we go to positive infinity. Should that be happening? No. So what we need to do is we need to clarify which side of 1 we're talking about. Part B is talking about the left side of x equals 1. So we're going to put a superscript of a negative sign, which means the value's less than negative 1. We're coming to 1 from the left, from the values less than it. And for the right side of 1, we're going to use a positive sign in the superscript, which means that we're talking about the values bigger than 1. So we're approaching 1 from the right, from like 3, 2, 1, as opposed to negative 2 or negative 1, 0, 1. Yes?
Are superscripts and subscripts opposites?
Yes, supers are up high, subs are down low. Everybody feel okay? So anytime you're doing one of these vertical asymptotes, you're going to end up with the super and the superscript minus and plus. When you talk about the left side and right side.
So this is the end behavior?
This is end behavior that we're doing right now, yes. Everybody okay? Who can tell me the last one? For D, x is approaching positive infinity, and the y is heading towards 2.
Is there a subscript over the, or sorry, superscript for the 2 because?
So you do not need one because it's okay for a function to have 2 x's that go to
Got
the
it.
same y, right? That's okay.
Got it.
So that's fine. We don't need to do it. We could, where you do again, you use the minus for the 2 below
Yeah,
and then a plus for the 2 above, but we don't need to.
got it.
It's not wrong to put it there, but we don't need it. It is wrong to leave it off the 1 for
Got
the
it.
x value.
Okay.
All right. One more end behavior example. Look at this crazy guy. How many end behaviors have we got here?
6.
6 of them. Ay caramba! Okay. Let's start cranking away at this. Again, these, not difficult because there's no computation. We're just kind of describing what we see with our eyes. We just have to make sure we're seeing the right things. We're looking at it the right way, but there's nothing to compute, there's nothing to calculate. We're literally just going, what, like what x coordinate is this arrow heading to, what y coordinate is this arrow heading to. So if I start at A, this arrow is heading to what x value? Negative infinity. And what y value? Also negative infinity, because the arrow is pointing to the left and down. Everybody agree? Okay. Oh my gosh. Now you did it. He'll worry about it later.
Yeah, seriously.
The thumbtacks.
Oh, shit. That's not good.
All right. We'll worry about it later. You just set it on, so it just sets on the ledge somehow.
Oh, I found it.
Oh, you found it? Found something? That'll do. Oh, there's a piece of tape is what was not holding it? Okay. All right. For B, what x value are we pointing to?
-1.
-1. And which side of -1 are we on? Superscript negative. And what y value are we pointing to?
Negative.
Mhm. Okay. Okay. Yeah, above the C, there says that x equals -1. How about at C? -1 plus, right? And going, where is the y going to?
Positive.
Positive infinity. Again, for the positives, you don't have to write positive infinity if you don't want. You can just write infinity. It's not wrong. I always write the plus, but it's not wrong to leave it off. It is wrong to leave off the minus. D next. What x are we pointing to? 3 from the,
Superscript?
yes, superscript negative. And what y value is this pointing to? Negative infinity. Now we're going to E. X is approaching, or x is pointing to? The x coordinate, the arrow is pointing to? 3.
Plus.
Good, 3 plus. And the y is pointing to? Positive infinity. And then our last one, F. X is pointing to? And y? Good. What do you guys think? This is where I want to stop today. I think this is enough. There's a lot of stuff. None of it was super duper complicated. Like there's not a lot of algebra going on, but there's a lot of rules to remember, a lot of stuff to compute. So at this point, you guys should be able to do 1 through 24.
Then how do you switch one to the graph?
Okay? My plan for the virtual day for conferences is I'll have a delta math for you guys to do, basically on this topic of finding these key features. So that'll be coming. We'll do a little bit more on these key features and putting them together into a graph next time. And a little bit more with the end behavior and taking the equation and coming up with the end behavior without having to see the graph first. Because eventually I'd like to give you like, okay, here's the features, draw the graph. So you have to go, back and forth, right? So that's the plan.
I'm not going to.